Greetings everybody. This is the second video for part 3 of the Chapter 8 Lecture Notes, and again we're dealing with collisions in 2 dimensions. And now let's look at example 2 for its an elastic collision in 2 dimensions. And what we have here is a proton undergoes an elastic collision with another proton that is initially at rest. And so obviously they have their masses are the same. And now what happens is the incoming proton has a speed of v1 initial in the x direction, and it makes a glancing collision with the second proton, which the second proton is initially at rest. And then after the collision, one proton moves at an angle of theta equal to 37 degrees above the x-axis, and the second proton gets deflected at an angle of phi below the x-axis, and one proton moves with the speed of v1 final, and the second proton moves with the speed of v2 final, as indicated in the figure. The M1, well, the masses are the same, but the first proton after the collision moves at an angle of theta above the x-axis. The second proton moves at an angle of phi below the x-axis. So we have v1 final and v2 final. And v1 final has an x and a y component, as indicated in the figure. v2 final has an x and a y component, as indicated in the figure. Now in this case, the algebra, and again, I want the final speeds of the protons, and I want the angle phi. So I want v1 final, v2 final, and I also want the angle phi. Well, remember, this is not we can't use those 1D elastic collision equations. We can't use those because that was for a one-dimensional elastic collision. This is two-dimensional. Well, the algebra in this one would be pretty involved. However, we can make use of the following. Whenever two objects of equal mass collide elastically in a glancing collision, so equal mass, see, two protons, they have the same mass, elastic collision, and it's a glancing elastic collision. So whenever they collide elastically in a glancing collision, and one is initially at rest, see, initially the second proton's initially at rest. Well, we know that we could prove it, but you can state it, you can accept it without proof. We know that their final velocities will be perpendicular to each other. So that's what right here in the blue. Whenever two objects of equal mass collide elastically in a glancing collision, and one of the objects is initially at rest, I know that their final velocities, v1 final and v2 final, will be perpendicular to each other, meaning that theta plus phi equals 90 degrees. Now the solution's much easier, because now I know the angle phi is 53 degrees, because theta was given as 37. So now the problem's much easier. Now apply conservation of momentum in the x and y directions. This is conservation of momentum in the x direction. v1 initial equals v1 final cosine theta plus v2 final cosine phi. Remember, the masses cancel because they're both protons, so the masses will cancel. Now conservation of momentum in the y direction. Well, the initial y momentum is 0, and the final y momentum is v1 final sine theta minus v2 final sine phi, because the v2f sine phi is negative. It's in the negative y direction. So I have equations 1 and 2. I'm going to solve equation 2 for v2 final. Take that expression, put it into equation 1. I get this equation. Cosine phi over sine phi is cotan phi. Okay? So I have equation 3. Solve equation 3 for v1 final, right here. And plug in the numbers and you get v1 final. Then once you know v1 final, go right here and get v2 final. So I have v1 final is a 2.8 times 10 to the 5th meters per second. V2 final is 2.11 times 10 to the 5th meters per second. And I know that for this particular problem, I know that the angle phi is 53 degrees because there are two objects of equal mass. It's a glancing elastic collision, and the second object is initially at rest. So I know that V1F and V2F will be perpendicular. The angle between them will be 90. So theta plus phi equals 90. And again, if you can understand where these two equations come from, equation 1, which is conservation of momentum in the x direction, and then equation 2 is applying conservation of momentum in the y direction. And then with the common technique, solve equation 2 for V2F, take that expression, put it into equation 1, right here, then right here. In the previous step, you have cosine phi, in the rightmost term, you have cosine phi divided by sine phi, which is cotan phi. So that has equation 3. Then you want to solve equation 3 for V1 final. And right here. Then once you know V1 final, use this equation to get V2 final. Alrighty.